Hi, my name is Vladimir Ivanov. I'm a software engineer working at Oracle on JVM compilers. So, for the past 2 years, I have been contributing to java.lang.invoke implementation in OpenJDK. So I would like to share with you what happened during that period and what are the plans for the future, what problems are still there, and where do we think we should move the implementation. So I'll start with a brief introduction. How does it look like? How did it look like before? How does it look like right now? Describe what have been done during 8 and 8 update releases for the past year and a half, and then talk about the future directions. So you should know this slide. So let's move on. So GSATA 92, which introduced method handles and java.lang.invoke, was integrated into Java 7, but it started back in 2005. From design perspective, there were a couple of major overhauls, and the outcome was that in Java 7 we got support for dynamic languages. So the 6 years led us to get right the design, but there are some weak points in implementation. So the design allowed to heavily optimize method handles, but it didn't work that well in all the cases. So there were problems with inlining. Generic invoke was slow. Charlie complained a lot about no class def found, and so on. And the implementation design wasn't that satisfying. So it turned out that the problem is the wrong IR for the VM. So VM optimized method handles, looked at method handle chains, but after some thought, it turned out that it's a wrong IR, wrong abstraction. So in 7 update 40 in 2012, John, Chris, and Michelle, they came up with a new implementation, java.lang.invoke implementation, based on so-called Lambda forms. So they introduced a clean separation between JVM and Java JDK code. So it healed many problems which were in original implementation. So no more no class def found exceptions, and it plays well with the JVM machinery. Lambda forms were translated into bytecodes, and JVM knows how to work with bytecodes. It worked with it from the very beginning. So what are Lambda forms? So how many people use method handles? Great, so you know that. So method handles, that's a typed, directly executable reference to either behavior or field method. And Lambda form is a symbolic representation of the semantic, invocation semantic of a method. So that's the separation. From the implementation perspective, Lambda form-based implementation allowed to clearly separate different levels. So if you are a user, you work with method handles, method types, you link in the invoke dynamic instructions with call sites. Underneath that, there is a whole new world of Lambda form-based stuff. And it interacts heavily with the JVM, but through a very limited set of VM primitives. There are linkers like method handle link to interface, link to virtual, link to static. There are a bunch of up calls and down calls into the VM, but the surface is very limited. And from the VM, it looks very clean comparing to the previous implementation. So what is Lambda form? how many people saw Lambda forms before? Wow. As many as used method handles. That's surprising. So let's look at the example. So here is a Lambda form for a method handle which does a field update. So it's a 4 statements. So like compute field of set, check cast a base, check cast a value. So A0 is a method handle, A1 is a receiver, the object where the field will be stored, and the A2 is a value which should be stored. So in order to do it in a type-safe manner, because you see, unsafe put object. We know what we are doing. So if we want to use just a field of set with unsafe, we need to ensure the value complies with the field value. So we do a check casts, and before we do an actual write. So it was a textual representation from the structural perspective. It's exploded representation. So you can iterate over it and pick and poke different information from this. A notable thing is that all the types are erased to basic types. So you don't see here java.lang string, java.lang whatever. You see object, long, int, that's it. And all, so it's basic type in a JVM specification sense. So all small primitives like bytes, booleans, shorts, chars are erased to integers. So it ends up with 4 primitives and reference type, plus void to represent return type. So if in order to inspect the Lambda form, there is a fine-grained representation for that information. And here I presented a textual representation. So all these functions are available as names, so both values and parameters are referenced through a names array. So here are 7, in total 7 values. So as we saw, Lambda form is non-executable representation of the invocation semantics. But it's not that helpful if we can't execute it. So how do we get the actual behavior? So trivially interpreting the structure, we can iterate over the values and invoking that functions and getting the result done. On the actual implementation, there are 2 ways to execute a Lambda form. So there is a special field, Lambda form, which points to a member name, which points to some method in the program. It's either an entry point to Lambda form interpreter, which generically implement that iteration over the structure of Lambda form, or for efficiency purposes, Lambda form is compiled to bytecode, translated to bytecode, and then JVM directly executes it. So Lambda form interpreter isn't supposed to be fast. It's trivially implemented in just a page of code. It looks clean, so it's not as fast as it should be. But it looks nice, I would say. And the bytecode translation is trivial. We can iterate over the structure and translate every statement into a bunch of bytecodes. So it's a trivial template translation. We see a function, we generate bytecode to invoke it. An interesting thing is that in order to get so here we have an unsafe. I think in this audience, more people used unsafe than method handles. So you know that all the methods are instance methods. So you have you should have an instance, unsafe instance, in order to invoke anything. So, and here we have a static structure. So we've injected unsafe instance. So how do we get that on bytecode level? Lambda forms are compiled into bytecode and loaded as VM anonymous classes. It's VM anonymous classes, not Java language anonymous classes. It's a specific VM instance. So it allows to instrument a constant pool and inject actual objects there. So when we load a class, we put unsafe instance there, and we can use it from the bytecode. So we generate a fake placeholder string load constant, but after the patching, it holds the unsafe instance. So we can safely cast it to some misconsafe and then use it. Since as you see from the name, it's VM anonymous classes, these classes don't have names. So you can't look up this class. You can only pass the reference to the class. So the consequence is that you can't reference that class even from the bytecode of that class. So it's impossible to access fields of the object of that class. So we don't have any other choice, because I was asked some time ago, come on, can we just add static fields to that class and use them? Why do we need to inject anything into bytecode? It looks hacky. So the problem is that since there is no name in VM manner, not in language, it limited the machinery we can use. But it looks really powerful, because we don't need to care about constant pool resolution, because we have already pre-resolved stuff at our hands, and we can just put it, pre-resolve it during loading. It's a powerful machinery. So let's move on. So let's look at method handle and Lambda forms again. And since method handles reference Lambda forms, there are two cases. We can have shared Lambda forms, shared by means of method handles share the same Lambda form. Or Lambda forms can be customized to some particular method handle. So let's look at some examples. So for example, again, field setter. So there are two calls. Here we're constructing two different field setters. So in first case, it's in completely unrelated classes. Fields are different. Field types are different. But we construct, we can reuse the same Lambda form to actually implement the behavior of that field. Because what matters here is that we use proper fields, for proper classes for type checks, and we use proper offsets. Otherwise, Lambda form can be reused. And this information resides in method handle, which is passed as A0, the first argument. And the VM just extracts, the Lambda form just extracts all necessary information from the method handle. So we can reuse the Lambda form, and so thus sharing Lambda forms among numerous method handles. On the other hand, it's limited, since we specialize for basic types. So here, if we have int and long fields, the Lambda form structure differs. So we use putInt and putLong. So we can't share the Lambda form. So the actual behavior is similar. So since GSAR method handles were introduced in 7GA, Lambda forms were integrated into 7U40, and in 8 we got a number of internal customers, let's call it that way. So Project Lambda started to use invoke dynamic, and GDK got a new JavaScript engine called Nashorn. Marcus and Attila did a great work moving that forward. So we got a lot of feedback on quality of implementation and the number of complaints. So the most notable complaint was the footprint. Lambda forms were heavy, and we generated lots of them. Startup, warm-up. From peak performance perspective, it was good. So we reached a pretty well level of performance. But from the startup and warm-up, it was too heavyweight, and the dynamic footprint wasn't great as well. So for 8U40, we started an effort called the Lambda form sharing. The goal was to considerably reduce memory footprint while preserving the peak performance at the current level. So what did we got? So on average, I used Octane benchmarks to gather performance statistics. So on average, on a relatively large benchmark like Box2D, there are around millions of method handles, and before 8U40, in pre-8U40 GDK, there are millions of Lambda forms constructed. They aren't translated into bytecodes right away, so there were about tens of thousands of VM anonymous classes loaded for that. After Lambda form caching effort, we got thousands, 3 order less Lambda forms, and classes on the same level. Like every cached Lambda form most probably will be compiled because they are heavily shared. So let's see what does it look like to share a Lambda form. So consider God with test. So it's a if then else but on method handles. So you pass 3 method handles, and you get a new and you combine them and get a new method handle which effectively implements if then else branch. On a Lambda form level, it looked in 8U40, pre-8U40 binaries as follows. So all these 3 method handles were injected into the structure. It means you can share God with test. It's customized for that particular method handle. And all these method handles are represented as bytecode as well. They're injected into the bytecode. So the bytecode isn't shareable as well. How can we change that? Why don't we move all these 3 method handles into a corresponding method handle for God with test and just load them from there and use? So this Lambda form shape can be shared. Problem solved, right? So what did we got with Lambda form sharing? Considerably smaller dynamic footprint, both in number of loaded classes and the metaspace size. Faster startup warm-up, because as you can see from the Lambda form structure, it's not cheap to construct them. They are quite complex entities. So then if you use it long enough, you get it compiled to bytecode, you load a class, and that's it. Then that class will be at some point compiled into native code. So reducing the number of Lambda forms significantly improved the startup and warm-up. And moreover, it allows us to further optimize, enable other optimizations, like Lambda form precompilation. So let's look at some numbers. So here are dynamic footprint. So the y-axis is how x. So for example, on box 2D, the metaspace consumption was 4x smaller than before. So it's 8U40 before Lambda form changes went in. And almost the same on, sorry for the color. It's the gray one doesn't look good here. So, and on the classes level, it's 4x less classes loaded for box 2D. So significant reduction in dynamic footprint.
Question, profile pollution.
I'll talk about that later. Wait for 5 minutes, please. I have a dedicated section for that. So from startup and warm-up perspective, it looks good as well. Most of the benchmarks benefit. For example, regexp 3x, 3.5x, faster. It's duration of the first iteration of Octane sub-benchmark. Splay suffers quite significantly, but that's mostly because the new bytecode shapes are heavier. There are more operations performed, and it doesn't get much from Lambda form sharing. Not many Lambda forms are shared in that particular benchmarks. So there are some regressions, but most of the benchmarks improve a lot. So regarding optimization of Lambda form precompilation, so before Lambda form caching, Lambda form execution started as interpretation in a Lambda form interpreter. And after 30 invocations, they are compiled into bytecode. So it allowed to considerably reduce the number of loaded classes because, as you saw, we had millions of Lambda forms, but we had only tens of thousands of compiled classes, of loaded classes for Lambda forms. After we started to aggressively share Lambda forms, we don't need to bother about that anymore. We have thousands of Lambda forms, so we can simply compile them right away and completely bypass Lambda form interpreter. So what did it solve? Charlie, do you know? Does it look familiar to you?
Oh, yeah.
Charlie complained a lot about stack consumption. And here is the stack depth for a trivial call, just a chain of depths of 2, so only 2 method handles in the chain. But for every method handle in that chain, we got 7 stack frames when it's interpreted. Wow. For deep enough method handle chains, it usually blows up stack pretty quickly. With the precompiled, when the Lambda form is compiled, it got just a single stack frame for every method handle. So we get down to 4 stack frames. Significant reduction in the stack consumption. And here is a peak performance. So some benchmarks improve, surprisingly. But it's not due to Lambda form caching, but due to related work on JVM I had to do to change compilation policy to play better with Lambda forms. So it allowed to improve some of the benchmarks, but there were some regressions. So the goal of the JEP in 8U40 wasn't completely met. We regressed on some of the benchmarks. So what were the problems? Profile pollution and non-constant method handle calls. They worked slower than they were before. So let's focus on that topics. So let's look at customized version and God with test. So we had all 3 method handles injected, and on bytecode level we got the following. Okay, we have God with test with the unbalanced if then else branch. the condition is always true. So when we look at profiling data, JVM sees that, okay, I never execute the false branch. Great, I can completely eliminate that branch from in the generated code. Wow, let's do it. If it's always false, we clearly see that in the branch frequencies. 100% the false branch was taken. But in a shared version, if the same Lambda form and hence bytecode is shared between unbalanced unbalanced God with tests combinators, JVM doesn't know anything about the branch frequency. Depending on the actual execution, it can vary from 0 to 100, whatever. So that's the profile pollution problem. Sharing, Lambda form sharing, and hence bytecode sharing caused less accurate profiling information gathered. So I came up with an idea how to fix that. Why don't we simply do a customized profiling on a per method handle basis, right? Why do? The question is how to do that. We want to collect that information only during warm-up, but completely bypass it during the optimized, when we warmed up and we execute optimized code. We want it to work in the same way as it works for JVM, on a JVM level. So some details how I did that. So I instrumented Lambda forms and introduced profiling logic there. So we can simply gather information on what values the condition, the test returns, and collect that information in an array of counters. How many times we invoke a true or false branch. So in order to get a zero overhead and optimized version, I needed some help from C2. So during profiling, during warm-up, if it's either we execute it in interpreter, there is a special logic which does the collection. But for example, in tiered setup, C2 can produce. It's not necessarily tiered, but for example, when we warm up a new method handle, it's not compiled yet, and we have a dedicated native method per method handle, per Lambda form. So in that case, we need to do profiling as well, and only get rid of it when we inline the whole method handle chain. So when it's warming up, it does profiling, but when C2 kicks in and compiles the whole method handle chain, it's optimized into a almost loop, because the counts of collected counts, they're injected into IR of the compiled method. That's it's no overhead on profiling after that point. I achieved that by introducing an intrinsic for that profile Boolean thing. Branch profiling is just one case of profiling. There are other profiling going on in JVM. So what about type profiling? My performance experiments turned out that type profiling isn't a problem after Roland did a type speculation in C2. And it completely, at least at all, type profiling doesn't affect the performance, peak performance in any way. So I got the same numbers or even better numbers with Lambda form sharing. And there is another case, the optimization counts. JVM collects information of how many deops happened at some particular BCIs and some particular places in bytecode. And it caused some problems, like the following bug, when the deops in God with test for unbalanced branches. So when we prune a branch and we at some point kick gut to it, we need to deopt, and VM records that information. And at some point, there is a logic when we do that too frequently, too many times, we just bail out and don't compile that method anymore. So performance, peak performance just dropped at the floor. So it's like very slow, became very slow.
Hey, Vladimir.
Yeah.
I'll channel Remy here and say that those of us who are using Lambda form or are using method handles, we generally know what we're doing. So just don't de-hop them, or don't ever give up on compiling them, rather.
Yeah.
De-hop, but
Yeah,
we're putting this together.
Yeah, yeah. But that's definitely a bug. It was fixed, but there is still no generic solution for de-optimization profile pollution. It's still possible. So if you see any problem with that, just file a bug. The other case is non-constant method handle invocation. Invoke exact, invoke generic. So let's look at the following example. So here we construct a local guard with test and then invoke it in an infinite loop. Of course, JIT can't inline it. So here we see method handle, invoke basic, receiver not constant. OK. We tried our best, but we can't do anything better. How does the native method, which is compiled for that particular method handle, looks like? So here we see for customized version, we compiled pretty good native method. We inline all three methods, test, true, and false branch. Good, pretty good. We pay extra only for initial invocation, but then we are fine. But in a shared version, it doesn't work as expected. So since we compile a native method for shared Lambda form, we don't know what method handle it is invoked on. So we can't extract anything from the method handle. And we have test, true, and fallback method handles there. That's the problem. It significantly affects peak performance. So the problem is that in a customized case, we compile a single native method for the whole method handle chain. But in case of shared Lambda forms, it splits into numerous small native methods, and the overhead of invoking them is quite high. So I observed overhead up to 20% peak performance regression on some Octane sub-benchmarks due to that problem. So how it can be fixed? So the interesting observation is that we don't need to customize the whole method handle chain. We can just customize the root method handle chain. And that's enough for JIT to know everything about the method handle chain. So if we customize only the root method handle, but leave all the other Lambda forms intact, shared, we get what we want. And there are only three ways to invoke a method handle. Invoke dynamic, where we already know everything about it, right? Because the invoke dynamic is linked to a call site instance, and JVM aggressively, optimistically optimizes through that. So it reads a value from the call site and inlines through. For invoke generic and invoke exact, that's the cases where we want to customize. So if a method handle is invoked through that reflection-like API, we just customize that method handle if it is invoked enough time. The customization is trivial. We can just overwrite since the Lambda form is customized, it means that it is used only with some particular method handle. So we can just override the method handle which is passed and inject the correct method handle right into the bytecode. So JVM knows what to use. So Lambda form sharing went into 8U40, and the performance fixes I talked about will be released as part of 8U60, which should be quite soon, at least on OpenJDK pages. The release date is somewhere in August. So when 8U60 released, if you are interested in method handle performance, give it a try, or use JDK 9. It already contains all the fixes I described.
Or hotspot comp?
Both. It's you can take early accesses. It went like in B50. I integrated them long ago.
Okay.
So let's switch to the future work. What can be improved further? So from the implementation perspective, I included 5 items. Let's go through them. So in 8040, there was an extensive effort to do Lambda form sharing, but it's limited to basic types. So we raise types to basic types and then use Lambda forms. So we don't do any boxing or varargs collection of the arguments. So all the basic types are left intact on the bytecode level. When Lambda form is compiled, it's left as is there. The main reason is to avoid any performance regression. So we want the method handles to be optimizable, to be highly optimizable. So we want method handle chains to go away in compiled code, and just it ends up like argument shuffling and actual invocation. So here, how it looks like on in a current implementation. So we have a call side with the basic types, and we don't change that basic types. We pass them as is through the method handle chains down to the actual invocation. If the argument started as int, it stays int for the whole method handle chain. How it could be improved? Why don't simply box them, right? And further erase them to objects, and do boxing and unboxing at the different ends of method handle chains. Box at the call side, unbox before actual invocation of direct method. It will allow us to specialize for arities. So like have a Lambda form for 1 argument, 2, 3, 4, that's it. Much smaller number of Lambda forms needed in that case. And why don't we go further and just collect all the arguments into an array and pass it as is? Wow, just a single Lambda form per behavior, right? It should further significantly reduce amount of Lambda forms needed. And I think it should allow to persist Lambda forms, and from ahead of time compilation, it's much more feasible than generating some per basic type specializations on the fly.
Performance then. Boxing and unboxing over that.
Yeah.
Sure, we want that to go away when we compile, right? Yes, Cliff.
Yeah, in order for it to go away, C2 has to have the right profile data. To get the right profile data, it has to have the different sites in line in a prior round of whatever.
Yes, sure.
To get site-specific profile data.
Yeah.
And so you're sort of encouraging or theorizing that first I'm going to crush it all together sort of semantically at a high level so I can get sharing.
Yeah.
Under the hood, it has to be exploded into parts to get private
Yeah.
profile data.
Yeah.
And then it's going to be jitted into parts to take advantage of profile data.
Yeah.
So, let's just skip the middleman here.
So the trick here is that we actually don't rely on profiling data here. We heavily rely on the fact that method handle chains are fully inlined. That's the key point to get reasonable performance for that. So we don't rely on profiling. We have all the necessary information at our hands. So you do boxing and unboxing as part of the same compilation.
We can go in the
Yeah. So the key point here is that JIT compilers should be able to reliably eliminate that boxing and unboxing, and look through arrays. So here we load the boxed values into array. Here we unload. Arrays right now are mutable. So there is no way to say it's an array with final elements. So compilers are conservative with optimizing arrays. We introduced stable annotation. How many people heard about stable? Okay. So a stable allows to constant fold loads from arrays, but it works only on field declarations. So if you load an array reference from a stable field, JIT optimizes it. But here we construct something new, local instance. And there is no way right now to annotate a value like a stable value. So more JVM work is needed to make that happen. Plus, from the startup and the warm-up perspective, during the interpretation, such sharing is quite heavyweight. So we need to measure how much does it save. Yes, John?
Are you going to mention frozen arrays, or shall I?
Yes, go ahead.
So one of the motivations for frozen arrays is to allow array erasure, array explosion to be more reliable, even if the array escapes along some paths, because then you can prove nothing bad happens on those paths to the payload of the array. Also, I want to say, for the record, that our colleague Frederick Orstrom prototyped array explosion and box explosion in JRocket several years ago, and it was the basis of his implementation of 292. So we have good hopes that it will work in our world too.
Yeah.
The main problem is that it's really hard to splice in sub-IRs into CO nodes IR in C2, as far as like when we try to do the same.
Okay. Yes, Cliff.
Yeah, so my C2 info is out of date, because I went and worked at Azul for a decade. I did a lot of stuff there, and totally it was, we have reliable box elimination. It was very straightforward to add. We totally would explode through arrays if there were new allocations, and you just did constant array indices to fill and to load out. That would have just pulled right apart as well. But I still think you're going to have to. Well, we should talk about profiling because I think you're
Yeah, let's talk about that offline. Yeah. So the next item is MethodHandle.asType. So right now, asType is the adaptation which is used to implement generic invocation. So exact invocation, MethodHandle invoke exact, requires that types of call side type and method handle types are equal in the sense that it's at the same time, exactly the same. But sometimes we want to adapt it slightly, like doing a cast. Like if you have an object on call side, but method handle has a Java. If you have an object, but you pass a string, so method handle types differ in don't differ too much. asType transformations allow to invoke method handles using inexact way when types doesn't match exactly. So constructing such adaptations are expensive, and we want to cache the result. Right now there is a single element cache on method handle. So when you do invoke generic on a method handle, by invoke generic invoke, I mean method handle method handle.invoke. That's called generic invoke. So if method types don't match, it tries to adapt the method handle using asType transformation, and the implementation caches the result. The problem is that if a method handle is shared and you try to adapt from different call sites with different types, you simply pollute the cache. Most of the time, you will recompute the adaptation. So we need to fix that, and most notably to hear your feedback. Do you see this as a problem? How important is that? How frequently do you do generic invoke when you share method handles? That's the data we would like to hear from the users, from you. Also, it's interesting to further reduce the consumption. Right now, it's almost, so after Lambda form precompilation, the amount of stack consumed is proportional to the depth of the method handle chain. Since we have a stack frame consumed per method handle. But for deep enough method handle chains, it still can consume quite a lot. So one of the solutions could be to customize, to compile a whole method handle chain and generate a single method for the whole method handle chain, some kind of inlining, but on a Lambda form level. I did some experiments on that front, and yeah, it was easy to implement, no additional work from on VM level. But the problem is that it almost completely defeats the Lambda form sharing benefits. So the amount of space needed is almost as much as we had with before Lambda form sharing, because we have usually too many indie call sites, invoke dynamic call sites, and we need to specialize for them. And also, VM anonymous classes are still classes. I'll talk about that a little bit later, but don't we need a more lightweight way to load code? Sometimes we don't need a
The smallest compile unit in class with a method in it. Come on.
Yeah.
Something good will fall out of our hotline class by I'm sure. And that can
Go get implemented, right?
yeah. I'll do it in my 20% project.
So the other direction could be tail calls. Most of the Lambda forms, they are tail calls. They have tail calls. So, for example, in that particular case, if we could tail call, it would end up with a with no stack overhead, no additional stack frame for the method handle chain, since all Lambda forms are they have a tail call at the end, so every next Lambda form they'll reuse. For example, as an exception, God with test isn't tail recurse, doesn't have a tail call for test method handle. So in that particular case, if you have a deep God with test method handle chain, you will have to preserve the stack frames for the tests. But other than that, in most of the cases, tail calls would help a lot here. There was a prototype in MLVM. The problem was the security, proper access checking, right? But I think we have a solution to that.
We have a good model for securing such things, and actually the prototype wasn't. The prototype solved most of the security problems. It was just a question of disrupting the rest of the system by integrating it.
Okay, yeah.
As well as, disrupting by integrating and then going through the optimization exercises.
Yeah, yeah. So there is we have an understanding how it could look like in the actual implementation. So it's possible to do. Lightweight code loading. So right now we have VM anonymous classes. It relaxes some limitations of classes, like when, so the idea is to remove the name. So you can't look up the class. It allows to disentangle the class loader and the loaded classes. So loaded classes can live on their own. So if you don't use a class, you can just, VM can just collect it. For the ordinary classes, the class lifetime is tightly coupled to the class loader lifetime, which loaded it. Removing the name allowed to relax that. But as I said, it's still a class. Do we already need a class? No. If we wanted to load a code, we don't instantiate that class, for example, but it's possible for an ordinary class to be instantiated if there is a constructor or we use some unsafe mechanisms to instantiate the class. Don't we want something like that? Construct a method handle, which points to some bytecode we provided. Something like a method with a constant pool, attached constant pool. Something like that. Does it sound appealing?
Yeah, we need some kind of shared concept construct that would get rid of a lot of the overhead that's like classes and arguments and stuff
Yeah.
like that. It's not crazy, but I mean, that's probably the way it has to be solved.
Yeah, yeah. Also, are there any, well, here is John from GC team. So how do GC engineers feel about VM anonymous classes?
We loved the reduction in the number of Lambda forms. That was wonderful. Made a lot of our work less necessary. This would be another good step.
Yeah, thanks. So classes, VM anonymous classes were a problem for GC guys because with the perm elimination, there was a meta space introduced to store classes. And the idea was based on the tight lifetime relation between class loaders and classes. And it doesn't work for VM anonymous classes. So for GC, there was a special treating of VM anonymous classes introduced, which complicated the life of GC guys a lot. Sorry for that.
I have a comment on sizing. Just as a matter of information content, if you look inside a random jar full of class files, as a rule of thumb, your method payload is probably about half, and your constant pool payload is probably around 1/3. And so the actual metadata for the class headers is relatively compact in terms of information content. Of course, it all expands into 64-bit pointers once you load it into memory, so then you get a different cost model.
Yeah. So the actual benefits, the actual benefits should be measured for sure. But it's most likely we can further relax the limitations. So we don't need the class most of the time. We just want a code to work with. Yes.
Point out, those of us who don't always have access to define an anonymous class also have to wrap every one of those classes in a class loader. Otherwise, it gets
Yes,
distributed and
yes,
never
yes.
goes away. So
Yeah, yeah.
there's a lot more memory overhead than just the class
Yeah,
itself.
yeah. Yeah, and another aspect of that change is to produce a public API for such functionality. Yeah. And regarding profile pollution, in addition to the optimization counts profiling pollution I talked about, so the solution which was implemented for Godwith tests isn't ideal. So though we fixed pollution on Lambda form level, if you share a method handle, you can end up with the profile pollution in that case. So the profile is collected on per method handle basis. So for every method handle, there is a special profile collected. But if you share method handle, you don't get a specialized profiling for every use site. Probably, if you do method handle sharing, you should be aware of that. Not sure it's important to be fixed, but there is another problem. Profile pollution causes problems for other parts of the system. For example, the most notoriously known is Streams API. They suffer a lot from profile pollution. John calls it loop customization problem. So you can Google up the good write-ups by John about that problem. So we have to find a way to fix that.
Cliff calls it the inlining problem, I believe, and he's
Yeah.
got good write-ups too.
Yeah, I'm working around it a different way. But I have loop fusion games where the inner loop is something different every time, and the outside is not streams, but it's distributed. Well, it's complicated. So I have to force inlining, and I'm doing it by full code rewriting, making new classes everywhere.
Yeah. So we'd like to encourage you to think about that, because it's a problem which is present in many different places. It manifests in different scenarios. So if you see that in your code, please think about how it can be fixed both on VM level and on other levels as well. Yes?
We showed that hotspot flag that Roland implemented with those levels of 1, 2, 3.
Yeah.
Does that get you some away there if you use that flag and crank it up to 3?
It could. So for streams, it won't help, I think, because you don't get inlining. What Roland did, it allows to flow the profiling information from top to down. If you have a polluted profile underneath, when the code is heavily shared, JIT can overload it with the more specific profiling on top. Yes, Cliff?
So Don can tell me if this is old news, but what I did as well was as I tiered C1 and C2, I put all possible profiling to C1, and it greatly encourages inlining to the expense of performance. And then in C2, took C1 profiling decision as tiles. And so C2 was always a superset of C1, but it would have site-specific profile info there. So very specifically, I was looking to clone the profiling sites to pick up site-specific profiles.
Yeah.
Anytime you had a pattern like that, I would tell C1 to damn well inline all these things, and then you got site-specific profiles. And then C2 would
Yeah.
take those specific profiles and know what the hell to do at each spot.
Yeah, yeah. That's a viable idea. I think Igor Verisov did a prototype of color Kali specific profiling, like in 2012 or something like that. Probably that's the way to fix part of the problem, or maybe most of the problem.
That has a problem. I'm blowing out your talk time, but just one sentence. That has a problem, Cliff, when the inner loop site runs in a different thread or in a different execution context from the original request, because then the JIT can't use all of the customized inlining profile information during its inlining. In other words, if with complicated reactive or work stealing frameworks, you might have your original custom request very far separated from the inner loop that needs customization.
Let's talk about it with a whiteboard or something in hand. It worked out pretty well for me.
Great. Let's discuss it offline. Thanks, Cliff. So, and regarding further extensions, so Paul, Doug Lee proposed, and Paul has been working hard for the past couple of years on var handles, they are designed as a safe, performant alternative to unsafe, part of unsafe methods. So initially they were they relied on the method java.lang.invoke framework. So they were different flavor of method handles, var handles. Not sure it will end up that way, but they initially they look like a natural extension of the API to provide a fine-grained access on a memory model specific aspects of field reads and writes. Regarding API enhancements, Charlie Nutter initiated a discussion a while ago, like half a year, regarding what would be good candidates for inclusion in java.lang.invoke. And it seems we are pretty sure there are a set of point enhancements in API which will help a lot to the users. So, for example, let's look at try finally. So right now there is a way to work around the problem. You can implement try finally with try catch and just append the finally logic on both in both exceptional cases and normal case. The problem is it's for the user. It's too much boilerplate code, and Charlie wrote a special library to ease the pain of working with method handles. And from the implementation specific, we can't generate it, or it's almost impossible to generate an efficient bytecode for that try finally shape. So on implementation, it blows into a set of Lambda forms, bound method handles, and it's really hard to extract the initial intent. If we have a try finally combinator, we could we could compile it down to the efficient bytecode with try, catch, finally. That's it. So. Also on a candidate list, method handle loop combinators and a couple of lookups. So if you want more details, feel free to contribute to the original mailing thread. So we are working on, so Michel Haupt plans to make some progress on that front. So stay tuned with that, on that. So we hope, I don't promise anything right now, but probably we can do something in the near future for that. And native calls are also a natural extension. John did a really good write-up a while ago about how native calls can look like on as part of Java.lang.invoke framework. And yesterday I did a demo of the prototype. We have been working as part of Project Panama FFI effort. It's, from my experience, it fit really well the framework. So for Java, we have all the separation ready, and to get a native calls, I just added a bunch of new entities like native method handle, native entry point. On VM level, it's just a new linker, link to native, and that's it. So if you are interested, I encourage you to download the Panama workspace and play with it. There is a test case with a bunch of POSIX calls implemented. So if you're interested in better FFI for Java, feel free to join to the effort. Try it, send feedback. We will be grateful for that. So that's it. Thank you very much. Yeah.
Since you're compiling all the way down to bytecodes now with all this, for those of us that are already generating anonymous classes, should we just skip the whole method handle Lambda form thing and just go right to bytecode?
You could, but
profiling and everything.
but yeah, VM does a lot of things to get it right. So we have, at least right now, the inlining decisions, the inlining and heuristics in the compilers doesn't work well with with the deep invocation chains, and we tweaked them for method handle chains. So if you just implement that yourself, you won't get as much performance as you could. So it should be fixed on.
But we could tweak our GWTs to be more aware of what we're doing, so we don't have the profile issue.
Let's discuss it offline. So I almost ran out of time. So I don't want to.
Tons of time.
Really? I'm almost over my hour. Okay, if we have time, let me know when we.
Why don't we take 2 or 3 more questions now, and then we'll go to break.
Yeah,
and
yeah.
People can continue that.
So regarding the question, so the question was, why don't we simply generate? If you are a user, why don't you simply generate bytecode yourself? The answer is in most of the cases it won't be optimized as much as if you use method handles for that, because we had to tweak the compilation pipeline to work well with method handles. For example, we have an exception for final fields optimization. So right now, final fields aren't optimized. Loads from final fields aren't optimized in normal code. But there is a special exception for java.lang.invoke classes. Just one case. The other is stable annotation.
There's also JIT thresholds that we can't cheat on. So.
Yeah, inline heuristics. Also, if you have too deep invocation chain, it will be pruned at like depth 9 or 10 invocations. That's a hard-coded limit.
We still suffer a bit that the bytecode is the original metric, so even if we can shrink a lot of bytecode transforms successfully, we still have like artificial limits that suddenly there is the drop because bytecode was removed anyway. So maybe IR size or something could be applied earlier or something like that.
Probably.
Inlining for indies.
Yeah.
I see that quite a lot, that I add one little thing to my combinator and I lose 50% of my performance, and that has to be like an inline drop.
Yeah.
There's depth cutoff, there's total count of bytecodes.
Yeah, bytecode is a bad metric. The code size, that's
Of
the same.
how well it optimizes.
Because you can look at rid of it, but you still look at bytecode size.
And then there's, well, as well, we also did a node count, internal IR node count.
Yep.
And started de-emphasizing bytecode count, because we get these things.
That's the way we hit that one too.
I thought just had to set that up and swing around.
Any other questions? Charlie, you had one.
I had one. So a lot of the profile pollution that you talk about goes away when we bind things to indie call site. We have a lot of shared method handles throughout JRuby. We do some invoke exacts, but generally, if you're running for peak performance, we're binding almost everything into indie call sites at some point. So it seems like one of the big things that would be helpful on the Java side is a way to do an invoke dynamic call site to a method handle so that we can have the same routing of the handles that you get from generated bytecode.
Okay. Brian, any take on that?
Oh, I'm sorry, I got it. So I didn't listen.
So Charlie asked for a way to inject invoke dynamic in Java code, right?
Right.
Did I get it right?
No one has ever asked for that before. How many people here are wondering why it's taken us so long to do this? Just a quick show of hands. Yeah, we think we may have a story for that. It's taken a long time. There are some completely non-technical but tricky issues surrounding that. But we think we have a way to a story that you can generate. You can express invoke dynamic in Java source code.
Right. Yeah, it was in the context of avoiding the profile pollution because we can actually anchor it to a call site then, rather than having to do the generic invocation tricks all over the place.
Right. Exactly. So yes, I would like to do that, and I think we might be able to do that finally.
Any other questions? Great. Thank you very much.